Alright, so there's nothing novel about this. I've seen this presented more or less this way before, but just want to walk through this. Okay, so given any random polynomial, right, so a times x to the n plus b times x to the n minus 1 plus c times x to the n minus 2, etc. up until the end, until you eventually get something times x plus some constant. What we want is when that all is 0 and x is our variable. Alright, now let's treat this, instead of looking at roots, let's treat it with logarithms. Okay, so we'll take log base x of the whole thing, right? So this is a notation that's a little bit better with just text, right? So this is basically means logarithm base x, okay, so xl of the whole polynomial is the same as log base x of 0. Log base x of 0, or log, any log, right, because we don't know what x is, it's undefinable. So let's substitute that for another form, and let's consider the fact that log base 10 of something like 2000 plus 400 is 3, which is if we just had 1000, log base 10 of 1000 would be 3. So that's basically telling us what n is, right? That 3 is correlating to n. Okay? So log base 10 of 2000 plus 400 is the same as 3 plus log base 10 of 2.4. Okay? So log base x of 0 in this case is the same as n plus log base x of basically just the string of digits in your radix x. Okay. So now you get this whole guy, instead of just equaling this undefinable log base x of 0, you get it being this. Okay? And now we can begin to work with things, because now let's bring it back so we can get that 0 working again, right? So what we're going to do is we're going to raise everything. We're going to raise x to these powers, right? So we get x to the all of that, right? Which at this stage, this doesn't look like we've done anything. And here it still may not look like we've done anything helpful. Kind of turns out that we don't really, but other than abbreviate the whole thing into a nicer system. Okay, so we get this. So now we can the logarithms cancel each other out, so we just get our polynomial back again, and that is now the same as n times just the string of the coefficients indicating a number with respect to the radix base, or the radix x. Okay, so now we can substitute 0 for this whole thing, so we get 0 equals this, or we can just rewrite it as this equals 0. But now we don't really need the n. The n doesn't actually do anything for us, because if we divide both sides by n, it really just disappears. We lose it from over here, and 0 divided by n is still just 0, so we can get rid of it, right? So we end up with a simpler form of the polynomial as just a string of digits, right? It's just your coefficients representing a number in radix n. And I don't think I mentioned it, but this is the notation I settled on for text to indicate radix, because this isn't really used for anything that I'm using very often or at all. So I was just like, yeah, it's right there on the keyboard. Let's just use that for this. Okay, it doesn't compete with anything that we're working with right now. That's fine. So that's what I'm doing here. So I'm using this to indicate the thing before it, separated by dots, is in base x. Okay. So now let's test if this works with an example. So we have this polynomial here, this quadratic that we can solve pretty easily, right? So we want two numbers that add up to 5 and multiply together to give us 6, so positive 2 and positive 3. Okay, and that means our x is negative 2 and negative 3. So now let's take the way we would normally do this. We would plug it in, right? So you get negative 3 squared is 9. 5 times negative 3 is negative 15, and then just 6, right? Or we can consider it as this, right? It's just this string with radix negative 3, which is exactly the same thing. And in both cases, we get 0. And then if we do it with negative 2, that also works. So this quadratic is a long form indication of 0 in bases negative 2 and negative 3. Okay? Now let's try it with a few different radices just so you can see that it's not just working for everything, right? So if we try 156 with radix 1, we get 1 squared plus 1 times 5 plus 6 gives us 12. That's not 0. That's not what we want. Now let's try it with maybe negative 1, because these are negatives, so maybe the negatives are happier with this. So negative 1 squared is 1. 5 times negative 1 is negative 5. 6. That gives us 2, right? The 5 cancels off 5 from that 6, so we just have a 1 plus 1, it's 2. Or 13. How about we try 13? Just something completely different, right? 13 squared is 169 times 1. 13 times 5 is 65. And 6. Add those all together, you get 240. None of those are 0. So this is confirming that this works. Also, you can see that what I'm doing, because this is basically like your ones digit. It's your radix to the 0 power, which is just 1. We're going to multiply 1 by this. This is our tens digit. So it's this squared, and this is like our hundreds digit. So it's this. No. This is our tens digit. So this is this to the first power here, and then this is to the squared. This is like 100, right? So in base 10, if we were doing it in base 10, we would get, actually I should probably do that. How about we just do that? I'll just copy this because I'm lazy. Swap it over to 10, and then we get 100 plus 5 times 10. Now look at that. In base 10, it just comes out 156, just like you would expect. So that's another way to think about what's happening here. It doesn't actually give us any shortcuts, but other than you can write it far more succinctly, right? And you can see that really what we're doing is we're just looking at numbers in different bases. We're trying to find the base that gets this sequence of digits to represent 0. And I'm not sure there's anything terribly profound about that. There's nothing I've discovered about that that's terribly profound. But it is a slightly different way of thinking about it. So that may, somebody thinks about that hard enough, that may lead us somewhere. But mostly I just think it's interesting that you can take this whole big complicated polynomial and really just reduce it to a string of digits. And it doesn't actually matter how you're representing the digits, right? Because in base 1, you can't represent 6 doesn't work in base 1, right? What is 6 in base 1? What is 5 in base 1 or base -1? What is 5 or 6, right? In base 13 and 10, 5 and 6, like conventionally the way you think of number bases, 5 and 6 make far more sense than they do in base 1. But it doesn't matter, it still works, right? Maybe we should try one with where 1 or -1 is a solution, just to show you that it actually does work. Let's drop this in somewhere over here. So let's do positive 3, -1. So we should get our solutions being 1 and -3. And now if I add those together, I get 2 over here. If I multiply them together, I get a -3 over here. So now we should be getting 1, 2, -3 in base 1 equaling 0, and 1, 2, -3 in base -3 equaling 0. So let's check this out. So okay, 1 squared times 1 is 1, and then 1 times 2 is 2, and then we get the -3. That does indeed equal 0. And now -3 squared is 9 times the 1. -3 times 2 is going to be -6, and then we also get a -3. So that is also equal to 0. So it doesn't matter. This doesn't care that 2 and -3 don't really make any sense in a normal way, the way you would normally consider a number system, with radix 1. So this does kind of show us that some of the way we think about things isn't quite right, because how would you have a base 1 number system? That can represent 2 or -3 or 6 or a billion or anything like that, anything other than 1. And yet it does actually work. And just polynomials just show us that. So yeah, there's that. But beyond that, I don't think there's probably very much profound in this, other than you can now write it more succinctly. And in base 10, this is literally what we do. But what we do is, to indicate 0, is we just write it as 0, but you could write it other ways. So if like, I don't know if I want to do another example, but if you made it so that 10 was one of your solutions, it's not going to work here. You'd have to change things. But if you made it so 10 was one of your solutions, then what you'll find is a representation in base 10. You're almost certainly going to have negatives occurring. But you're going to have a string of digits that in base 10 is sort of another name for 0 in base 10 than what we normally indicate 0 as. So like that alone is interesting. So I feel like that those little things that are happening in that, I think they're interesting enough to make this worth commenting on.